quantum mechanics and possibly quantum field theory as well. But I'm aware that I'm speaking in a series of seminars, and that where I'm speaking, this is a very eminent place where lots of people are with expertise in nonlinear systems. And so my second part will also be on how these ideas can then be applied in nonlinear systems, and in particular in nonlinear integrable systems. So that's the rough outline of my talk. There are two parts. Yeah. So I will start with quantum mechanics, and I want to remind you why hermeticity in the first place. So we will be talking about non-Hermitian systems. Yeah. So what is special about them, and why is hermeticity a good property to have in the first place? Yeah. And that's sort of explained here. There are 2 points for this. The first one is hermeticity guarantees the reality of the spectrum. Yeah, and this you can just see here by looking at these first 2 equations. So I have here just the time-independent Schrodinger equation, and then I have the conjugate. And if I multiply one of them from the left by the state psi, and the other one from the right, then we get these 2 equations here. And if the Hamiltonian is Hermitian, I can just subtract them, and then we get this equation over here. Yeah. And in Hermitian theory, this bracket is non-zero, and therefore the eigenvalues are guaranteed to be real. Yeah. So if you have an Hermitian theory, you can be sure you have real eigenvalues. And moreover, hermeticity also ensures the conservation of probability densities. Yeah. So if I have here a standard time evolution, I have a time-independent Hamiltonian, and I evolve a state from t equals 0 to some arbitrary time t, then this is my evolution operator. And if I calculate now the probability here, then you see here in the middle, I have a term e to the IH conjugate times t times e to the minus IHT. And you see, if H is Hermitian, then these 2 terms just cancel each other out. And probabilities are the same at time 0 and at any other time. So they are preserved. Yeah, this is the other important property that is guaranteed by hermeticity. And so usually when we have non-Hermitian theories, we think about dissipation. So probabilities are not conserved. Yeah. But this is not the type of system I want to talk about here. And this is not the type of system which is sort of fashionable a little bit at the moment. Because they are generally open. And here we are talking about a system that is self-consistent. Yeah. Leaving aside if quantum mechanics itself is self-consistent, but to that level that quantum mechanics is self-consistent. But it turns out, and this is in fact known for a long time, namely since 1960, it goes back to a paper by Wigner, you don't need a Hermitian theory to achieve all this, to guarantee all this. So I just summarized this here. I will explain this a bit better later on. Yeah, so if you have an operator O, yeah, this is left invariant under an antilinear involution, and I will also explain what that means. I will just summarize the result here. And if the eigenstates of this operator are also eigenstates of the involution operator, then this operator is guaranteed to have real eigenvalues. And you see in this statement, it's never mentioned that this operator has to be Hermitian. This is a general statement. So this is a statement that goes beyond the hermeticity property of this operator. Yeah. And you can then also make sense of this theory and turn it into consistent quantum mechanical framework, and I will also explain this. Yeah. So it traces back the first idea about the spectrum, or the insight into the spectrum, traces back to the 1960s paper by Wigner. And then there were lots of mathematical considerations at the time, but the first sort of physical considerations can be found here in this later paper, starting in the early 90s. Yeah, and it's still going on until this day. Yeah. So as I already said, there's nothing said about this operator to be Hermitian. It holds for any operator. And here's sort of the classical seminal example. Yeah. It goes back to this paper by Bender and Böttcher from 1998. This is really when this area took off and when most people appreciated that there's probably something behind these ideas. And it's a non-Hermitian Hamiltonian, has a very simple potential. You see here is a kind of deformation of the harmonic oscillator, and it has an Ix to the epsilon, where epsilon can be any real number. And here, this is taken from this Bender-Böttcher paper. You can see the spectrum is real and discrete as long as epsilon is greater or equal to 0. Yeah. And here, they sort of merge. If you go below 0, then the eigenvalues become complex. I will also explain this more what happens. Yeah. But you see here, if you take epsilon to be 1, yeah, that's the most basic example. You have Ix to the power 3, which is not Hermitian. Yeah. Even if you take epsilon equal 2, then of course we get an Hermitian Hamiltonian. We get I squared, so it's -1, but we get x to the 4. So we have minus x to the 4, which would also be considered not a useful Hamiltonian because not bounded from below. Yeah. But in this context, one can make sense of all these type of Hamiltonians for all epsilons that are greater or equal to 0. I should say this was not the first example in the literature. If you look back in the literature, non-Hermitian Hamiltonians appear all over the place, but I would say they have not been treated properly at the time. Yeah. So here's, for instance, I will not go into these models, just to list them, just to give the idea that such theories have been around. So here is a lattice region field theory, which was studied in the 70s for reasons to reproduce hadron spectra, etc. But if you look at this Hamiltonian and you just specialize it to one side, you get almost this Ix to the power 3 Hamiltonian here. Yeah, so there's this potential appearing here. There's sort of other terms as well. Yeah, but this non-Hermitian piece, which was essential in this example, is already there. Yeah, and that's going back to 1975. Yeah. And you can search in all other areas, you will find non-Hermitian Hamiltonians, and they were not designed to describe dissipative systems. Yeah. So for instance, here, this is a quantum spin chain. That's, if people know about conformal field theory in the continuous limit, it's related to conformal field theory with central charge -22/5. So that's the main reason why this was studied. To elaborate on this connection. There are also field theories. Yeah, so here's a Toda field theory, and in particular, the one where this coupling constant is taken to be purely imaginary, and that makes the Hamiltonian non-Hermitian. Yeah, they have been studied extensively because the scattering theory in the quantum field theory is involving the famous Young-Baxter equation, and there's nice mathematics behind which can be solved by quantum groups, etc. Yeah, so also in field theory, one has studied non-Hermitian theories for a long time. And there are also string theories. Here's one example which naturally lead to non-Hermitian systems. Yeah. But you don't have to start from a sort of Lagrangian Hamiltonian point of view. You can also start from a space, and you can start by deforming sort of space-time structures. That's very interesting. And one example here is to deform the canonical commutations of the Heisenberg relations. Yeah. And if I solve this equation now for x and p for momentum on space, we get some relatively complicated commutation relations, but you can take a non-trivial limit and send q to 1, and then it becomes a much simpler digestible relation, which is useful to work with. Yeah. And you see here, if I now want to represent this x and p, I'm sort of naturally led to represent x and p in this way, where p0 and x0 satisfy the standard commutation relations. Yeah. If you plug this back in, that will reproduce this commutation relation here. Yeah. And you see here when tau is sort of this deformation parameter, when tau goes to 0, then you get the standard canonical commutation relations between x and p. And they are interesting from a physical point of view because they lead to minimal length and etc. These are aspects I don't want to discuss now. So important here is that you start from some commutation relations. You are led to some non-Hermitian representations of this algebra. Yeah, so they're non-Hermitian. If I take here now the conjugate, or if I plug them into the standard inner product, then these operators are non-Hermitian. And that means if I take a Hamiltonian that is expressed in terms of coordinates and momenta, then this will naturally be non-Hermitian. Yeah. So here's the simple example of the harmonic oscillator. If that harmonic oscillator lives on this non-commutative space, then you see here, this is all now converted into standard x and p's, then this will be naturally non-Hermitian. Here you see this term is non-Hermitian here. Yeah. But one has to be careful because there are also sometimes Hermitian representations for these algebras. Yeah, so this is less obvious. Yeah, that these commutation relations, they can also be presented in a Hermitian way. Yeah, that's not always the case, but in here this is the case. And if you work out the physics, that's of course exactly the same. And I will say what you need to do when it's not Hermitian, as opposed to when it is Hermitian. I will explain that a bit later. And there are generalizations to higher dimensions. You can put these algebras also onto a two-dimensional space, onto a three-dimensional space, and the picture will not change. Down here, you see, you get non-Hermitian representations now also for x and for p as well. Yeah, this is just two-dimensional, but you can generalize this as well. So this much as an introduction. These theories are all over the place. And you can get to non-Hermitian theories in various ways. Quantum theories, for the moment, I'm talking about. So the next question is, well, how can we explain the reality of the spectrum and what is behind? And there are maybe two proper explanations. Yeah, the last one, supersymmetry and double transformation, it's not so much an explanation, but it's also something one can exploit. And I will explain how that works. So the first one is pseudo quasi-Hemiticity. So, and that simply assumes that if I have my non-Hermitian Hamiltonian capital H, then there is some similarity transformation. And that's usually referred to as the Dyson Map, because the first paper on this goes back to Dyson from 1956, that this can be mapped to some Hermitian Hamiltonian. So if I'm conjugating this Hamiltonian, so I'm assuming now that small h is Hermitian, so h dagger is equal to h. I also conjugate this right-hand side, and then I'm just multiplying from the left and right-hand side with the eta and the eta minus 1, and we get a new object, which is rho, which is eta dagger eta. And this is what is called the Quasi-Hemiticity relation, going back to very old papers by Dieudonné, just looking at this relation. So this object rho will play the role of the metric, as I will explain a bit later. Yeah. And then, of course, I explained already that h, when small h is Hermitian, the eigenvalues are guaranteed to be real. And this is just a similarity transformation. And we all know similarity transformations do not change eigenvalues. So therefore, as long as this map eta is well defined, the eigenvalues of capital H will also be real. Yeah. Of course, to say eta needs to be well defined is the catch here. Yeah. So not all non-Hermitian Hamiltonians have real eigenvalues, of course. So here's a bit of terminology and history. There are two notions here, which are usually just exchanged and used synonymously, but strictly, if you check the mathematical literature, they are not. Yeah. So, and here is this sort of distinction. Quasi-Hemiticity goes back, if you trace it back, goes back to a paper by Dieudonné. He was the first one using this, and he simply assumed this kind of intertwining relation, where it's not assumed that rho is invertible. Yeah. This already said rho needs to be a metric, so we would like also rho to be positive definite. That's guaranteed when you use quasi-hermeticity, whereas when you use the notion of pseudo-hermeticity, which goes back to these papers originated by Froissart, then this is not guaranteed. Yeah. So usually in this context, people don't distinguish this language so precisely, and actually people usually talk about quasi-pseudo-hermeticity and usually assume both of these properties, namely what is written here in the first column, namely rho is invertible and rho is also positive definite. Yeah. So that's one side of the story. Yeah. And the other side is PT-symmetry. So I already alluded to this, that you need this antilinear symmetry, and PT is something we all know. X goes to minus X, P goes to P. If I split this up into P, yeah, then the first transformation is a parity transformation. Yeah, so X goes to minus X, P goes to minus P, and time reversal. Yeah, X goes to X, yeah, and P must go to minus P, and this is crucial here. I goes to minus I. Yeah. Where does that come from? Just think about, an easy way to think about it is you think about X commuting with P, and then on the right-hand side, you get an I. So if I want this to be invariant, and if I send on the left-hand side X to minus X, then I have to compensate this on the right-hand side and send I to minus I. There are other reasons for this, but that's a simple way to get an intuition where this I might come from. Yeah. So PT, because of this property, yeah, is antilinear. It's an antilinear operator. So if I have a linear superposition of two states, then if I pull PT through and act on the state itself, it will conjugate the complex constants in front of these two eigenfunctions. Yeah. So that's the property of antilinearity. And also what I have to assume, that PT is a symmetry of the Hamiltonian. And what is nice is that's usually really trivial to read off. Yeah? Sometimes it's more complicated, but in general, you can just read this off. And also the eigenfunction of the time-dependent or of the eigenvalue problem. Yeah? I want this to be a Hamiltonian, but it doesn't have to be a Hamiltonian. These eigenstates need to be eigenstates of PT as well. And if we have these three properties, yeah, commutation of H with PT, the eigenstates of the nonlinear Schrodinger equations are eigenstates of the PT operator, and the fact that PT is antilinear, that guarantees the reality of the spectrum. And the proof is just one line. I can show this to you. Yeah, so I start here with the time-independent Schrodinger equation. I'm using the fact that I can replace phi by PT phi. There could be a phase here, but to make things simple, I just choose the phase to be 1. But it also works when you have a phase. So I replace phi by PT phi. Then I use the property that PT and H commute. So I pull the PT to the left of the H. And now I'm using again the time-independent Schrodinger equation, and I replace H phi by E phi. And now comes the antilinear property into play. When I pull this through now, this will conjugate the eigenvalue to make it the complex conjugate. And now I have PT phi, which I can replace again by phi. And therefore, if you look at this equation, the eigenvalues are guaranteed to be real from these three properties. That's the simple one-line proof. And the conditions you need. What happens when I give up some of these properties? Namely, I still have a PT-symmetric Hamiltonian, but I give up this second property that the eigenstate of the Hamiltonian is no longer an eigenstate of PT. So I'm giving up this property here. Yeah. And that means instead of PT acting on phi 1, here I just get some new phi, which I call phi 2. And each of these phi's will have their own eigenvalue equations. Yeah. And if we just use now this fact. You see here what happens in this case is that the energies are complex conjugate to each other. Yeah. So the eigenvalues of phi1 and phi2 form a complex conjugate pair once I give up this property over here. Yeah. If I reinforce this, well, then this will just be phi1 map to phi1, and we have the argument that we had before. So these are the scenarios, and there's a special name for this point when the PT symmetry breaks. I mean, when suddenly this property kicks in from being an equal sign to an unequal sign, that point is called the exceptional point. So, but you see, PT, this I also want to stress, is only an example of this symmetry. I never used the fact that this is in fact PT. I just used the fact that this is an antilinear operator. So here's the general picture. So real eigenvalues are drawn here in solid lines, and imaginary parts are drawn in dotted lines. And the orange region is the PT symmetric region. So we have phi1 and phi2 being eigenstates of PT, and then at some point they may merge, which usually you don't have in Hermitian theories. We know that there's avoided level crossing from von Neumann, but when you have non-Hermitian theories, they can cross now into the complex plane. And as I explained in this part here, what usually is referred to as the spontaneously broken regime, we have complex conjugate eigenvalues. Yeah, so these two real eigenvalues, they merge and become complex conjugate. And this point here on this line, this is called the exceptional point. That's the general picture to keep in mind. This is what is happening. As a function, I should say, some arbitrary parameter lambda, which is a parameter in your theory, you can tune so that this spectrum will actually change. Then there is another possibility, and I think I will be a bit fast on this. I can see time is running fast as well. That's making use of supersymmetry, or in quantum mechanics, I should say. Yeah, that's an analog of supersymmetry applied in quantum mechanics, going back to papers by Witten and so on. And in mathematics, people refer to this as Darboux transformations. And what these transformations do is there's a very controlled way to map one Hamiltonian to another Hamiltonian. Yeah, and this is what we had before. We mapped an Hermitian Hamiltonian small h to a non-Hermitian Hamiltonian capital H, or the other way around, depending where you start. Usually we start on the non-Hermitian side. And that's the same here. But this is another transformation. It's specified here. You can take some Hamiltonian, factorize it, and then you have these, what one refers to as supersymmetric charges, and you can relate the two Hamiltonians and also the solutions of these systems to each other by these charges. And what is important for this context here is that you can have the scenario that one of the Hamiltonians is Hermitian and the other one is non-Hermitian. And when this property down here holds, then one of them is real and the other one, or Hermitian, and the other one is non-Hermitian. Yeah. So this scenario can also be achieved in this setting, which is, if you want, it's also an explanation, but they're not entirely isospectral. Usually you lose at least one state, the ground state, but you can also lose much more of the spectrum. Yeah. So it's a slightly different scenario, as I explained before, where the spectra match exactly and you have strictly iso spectral Hamiltonians. So that much for the spectral analysis. Yeah. So how to formulate a consistent quantum mechanical framework for these theories? Yeah. And what we need is orthogonality. We need to define what are our observables in our quantum mechanical system, and we need to know also, is this unique? And it turns out it is not. Yeah. And then I will just make a few comments on the technicalities, how to do that actually. So I already explained this step to argue that the eigenvalues are real, which I carried out for non-discrete states. Now I take discrete states, and you see here I can draw more conclusions from this for a Hermitian Hamiltonian. When n is equal to m, then I get the energies have to be real, but when n is not equal to m, I can deduce that they are actually orthonormal. Yeah. If I normalize them as well, yeah. But psi n and psi m have vanishing overlap. Now, what happens when I have the non-Hermitian Hamiltonian? Well, I normally cannot move. So this is what Hermeticity means. I can move a Hamiltonian or any operator from the right to the left. Yeah. So I'm not worried about here about proper self-adjointness, where we have to also consider the domains where these operators are defined. Yeah. So it has to be ensured that the domain on the left and on the right are well defined, etc. I will ignore this here. Yeah. So just as a notion of hermeticity, I can move the operator small h from the right to the left. Yeah. And this is in general not true when I have a non-Hermitian Hamiltonian. But if I redefine my inner product, yeah, so this is like, I call it here the Eta Inner Product, has different names. And if you include here an eta squared, where I assume that eta is Hermitian, you don't have to do this. The general notion, you see, this was this operator I derived up here from this pseudo-hermeticity property. So if we have the similarity transformation, then it is guaranteed that there is such an operator. And that's the operator we can insert here. If I assume that eta dagger is eta, then it becomes just eta squared. Yeah. So that's what is done here. And if you define this inner product, then you can actually move H, capital H now, the non-Hermitian H, from the left to the right in your inner product. Yeah. And then I can just use, when I'm able to do that, then I can just use the same argument I explained here on top with the Hermitian operator. So now we assume this pseudo-hermeticity, and we can derive this new metric. Yeah. And here's again a very short proof. I will not go through it just to save a bit of time. And just using this property here establishes that with this redefinition of the metric, I can move capital H from the left to the right, and therefore it becomes an Hermitian operator in this metric. Yeah. So we have now a good framework to calculate quantum mechanical properties. Yeah. So we have guaranteed that if these maps, if they exist, then we have also real eigenvalues, and the eigenstates are orthogonal. Yeah. So that's guaranteed by the fact that they are Hermitian. We have to define what observables are. Yeah. And in Hermitian theories, we know that observables need to be self-adjoint operators or Hermitian operators. And this is what we just established. Yeah. We have seen how to do this, and we can extend this now to the non-Hermitian scenario with this new inner product. Yeah. So here I wrote again eta dagger, and I don't assume that eta is Hermitian. And we can take any operator now from the left to the right, and therefore they are Hermitian. Yeah. So the Hamiltonian was one example, but this is more generic. So we can relate them to the operators to the Hermitian theory. So operators in the non-Hermitian theory are related to operators in the Hermitian theory also by this similarity transformation. And they're conjugated by this rho, by the metric. A little warning. So sometimes now, so we go back to this standard simple example of H is a half p squared plus I x to the power 3. This x and p, from what I just said, are not observables. Yeah. But what are observables in the non-Hermitian theory, yeah, are the transform quantities, which are called here capital X and capital P. Yeah. So if eta acts in some non-trivial way on X and P, then we get something very complicated. And in fact, in this theory, Ix to the power 3, this is very complicated. In that case, we don't even know exactly what eta is. We just know it in a perturbative fashion. Yeah. So these expressions here, they are extremely complicated. Yeah. So how to do this, well, it should be clear now that the central objects here are these etas and the rhos. Yeah. So we have two options. We can solve this relation here, the similarity transformation, and then we just calculate rho directly, or we calculate rho from this quasi-Hemiticity relation that conjugates H. Then you find rho. But the downside is, in that scenario, you have to take at least the square root of rho to find eta, yeah, which you need to calculate the corresponding Hermitian Hamiltonian if you want to. You don't need it. Everything is already defined once you have eta and rho. Yeah. And technically, this is very complicated. It involves complicated commutation relations, and often this is only solved perturbatively. Yeah. Moreover, the solutions are not unique. You know? So that means, given a Hamiltonian, your physics is not unique, because you can associate a non-Hermitian Hamiltonian. You can associate different types of physics to it. Yeah. So there's a way to make them unique, yeah, and that is fixing another operator. Yeah. So you can do this, but initially your physics is not uniquely defined. Yeah. In some sense, this is also true in the Hermitian theory, but there we make a natural choice. The inner product we are taking there is the very natural inner product, and we don't really think about it, but we still make a choice. Yeah? Whereas in a non-Hermitian theory, we have many choices. So just a sort of a little disclaimer here. At the beginning, when non-Hermitian theories were considered in this way, people were sort of saying, "Oh, this is a new type of quantum mechanics," and there were all kinds of misleading statements around. And I just want to make a disclaimer: that's not the case. Yeah. This is standard quantum mechanics, and we just give up the restriction that the Hamiltonian has to be Hermitian. Yeah. You can find many textbooks, and there will be written. It's written there that well-defined quantum mechanical Hamiltonians have to be Hermitian. That's not the case. Yeah. So here are some examples, and given how time is running, I will just flash them a little bit. Yeah. So here's a two-level system, a simple Hamiltonian in terms of Pauli matrices. Yeah. That's, of course, something you can easily calculate. You can calculate the energies, eigenenergies, and the eigenstates. And you see here, this is not always real. Yeah. And it may break down. But if lambda modulus is greater than kappa modulus, yeah, you see immediately that I should say, what is PT here? PT is the sigma z Pauli matrix, and the time the time reversal is the complex conjugation here. It just conjugates this, and if you look at this operator will commute with H, and it's of course anti-linear. And if you work out the action of this operator on the eigenstates, you will see their eigenstates in fact once lambda modulus is greater than kappa modulus. But if I go to the other regime, you see, then I pick up another I here, and this is no longer true, and then we get complex conjugate eigenvalues, which we also get here from the direct calculation. Yeah. So this is all consistent and explains how these equations work. Yeah. My claim is that when you switch on time, then also in this broken PT regime, the eigenvalues become real. Yeah. Here's another example of an infinite dimensional Hilbert space that's more complicated. So this is a coupled harmonic oscillator, and this term introduces the non-hermiticity. We can express this in terms of an algebra. Yeah, here's the algebra for these operators, and then one can work out things more easily. And here is the corresponding Dyson map down here. And you see also here, it will break down at some point. Yeah. So you can solve, it's often a technical challenge, all sorts of models, and you can find the Dyson map, and you can find the metric. And depending on where this is defined, you can also make statements about the spectrum. For the time-dependent case, things are a bit more complicated. I will just indicate this. So we now start with two Hamiltonians that are explicitly time dependent. Yeah. So like the Stark Hamiltonian, you take an atom and couple it to an electric field or something, and then we need to consider the time dependent Schrodinger equation. And in this case, this former relation here, where we had this similarity transformation, needs to be replaced by this equation, which we usually refer to as the time-dependent Dyson relation. And there's this additional term, which is a bit like a gauge. If you think about gauge theories in quantum mechanics, then you will also get such a term. But here the crucial difference is the Dyson map is a non-unitary map. So this is not just a gauge. Yeah, this is a non-trivial equation. And likewise, this quasi-Hemiticity relation we had, which was this intertwining relation, needs to be modified in this way. Yeah. So this comes out very directly. And that means immediately that H, if you look at this relation, H is not an observable because it's not related by the eta to each other. That led to a lot of controversy at the beginning when time-dependent systems were studied, and people said, oh, this is not possible to set up because H is no longer observable. Well, that is true, but why should it be? So now the consensus is H is the Hamiltonian, which satisfies the time-dependent Schrodinger equation. But for the energy, we need to define a new operator. Yeah. Usually this is the same in Hermitian theories, but in non-Hermitian time-dependent systems, H, capital H, the Hamiltonian, has no longer this dual property of being the Hamiltonian and the energy operator. There are two different operators now. So that's what I said here, and this is the new object we can define. This is the time-dependent energy operator, and that operator is observable. And what is interesting is there are now various applications. So here is a very famous one that is in optics. So all these ideas that were developed in the quantum mechanical scenario can be applied now to optics by just a formal analogy. Yeah. So here is the Helmholtz equation in optics in a paraxial approximation. And if I identify here Z as T, then this looks formally just like the time-dependent Schrodinger equation. And there we have a natural way to introduce complex potentials. And this has been, and it still is, explored in laboratories all over the world. And in 2015, Nature considered parity or PT-symmetry in optics as one of the most of the 10 most important discoveries in the last 10 years. So between 2005 and 2015, that was considered by these authors as the most important discovery. So there's a lot of experimental verification in optics going on. And so this is not just a theoretical game. This is being explored in laboratories. And what is really interesting, in my opinion, is, so here's an example of a time-dependent coupled oscillator. Here's a Dyson map. I will not go through the technicalities. We can find it, and we can now calculate properties. And what is interesting is, this is, I alluded to this, is this statement, that the energies become now real in the broken regime. So in the time-independent case, this regime becomes sort of unphysical because we have a growth and loss at an infinite rate, and one of the signs doesn't really make sense. We usually throw this away, whereas when we have time-dependent systems, this regime also becomes meaningful. Then one can calculate quantities such as, for instance, the von Neumann entropy, and I will just show you now the results. So here's a simple example of a boson coupled to a bath, and I want to calculate the von Neumann entropy in that system, which is time dependent. And this is completely solvable. And what we expect in a Hermitian theory is what in this famous paper by Eberle and collaborator is called the sudden death of entanglement. So usually when you have entanglement, there is a really sharp decay if you look at the entanglement as a function of time. And that effect is called sudden death. But in non-emission theories, that's no longer the case if you go across the PT regimes. So here is the von Neumann entropy for the system I showed you in the PT regime. And you see here, this is what we expect. It's a sudden death. Yeah, it's going very sharply down, but it's oscillating, it's reviving. Yeah, but still there is always this sharp decay appearing. And of course, it changes when we change the length of the spin chain, but that's another story. It's still a sharp decay. However, when we are at the exceptional point, this is kind of prolonged. So it still decays to zero, but it's prolonged. But now we can also make even sense in the PT regime, and in that regime, we obtain a finite value. So potentially, this can be very interesting in applications in quantum computing, where you have to worry about decoherence, etc. Yeah. So this is no longer decaying to zero. You can reach now in this regime a finite value. Yeah. So this is being explored still quite intensively, and they're very interesting effects happening. So for this part, which was meant to be my first part, and I'm aware time is running, you can find more details in this paper. So now comes the second part of my talk. Many of you will have waited for this because this is a department of nonlinear science. So here are some examples of how these ideas can then be applied to nonlinear systems, nonlinear integrable equations, etc. So here's one of the standard equations, the KdV equation, and there are many ways to use now PT-symmetry. So initially, we looked at deforming differentials and finding new systems. But this is actually more complicated than what I'm explaining here, and what was done actually later. We did the complicated stuff first in some sense. And these deformations turned out to be often non-integrable. Whereas this one is a very simple example. We just look at the KdV equation and we take U to be complex rather than real, and then you can just decouple the equation. You can look at it as a coupled system of equation if you like, and study this model. Yeah. And this system is PT-symmetric. It's stated here. So U just goes to U. It's a very simple PT-symmetry, but it can be realized. And in this case, we maintain integrability. There's still a Lex pair we can use, and we can study this model. We know how to find solutions for these complex models. One of the methods is here, Rotha's direct method. We have to bilinearize the equation and calculate the so-called tau functions. Yeah, I will also not explain this, just to take away from this slide that solutions can be found. Yeah. And here's a one soliton solution, and you can see it's complex, and it's PT-symmetric. If you look at the function, if I send x to minus x, t to minus t, then for instance here in the last term, this is the interesting term to look at. We pick up a minus sign from the hyperbolic sign, and that's compensated by picking up another minus sign from the I. And they were in fact studied by other people as well. Kare and Sashena looked at another way to construct PT-symmetric solutions to these systems. They sort of assume that they can be expanded in terms of hyperbolic trigonometric functions. And they had a special case, which is just corresponding to our solution when you set this arbitrary parameter theta to pi over plus minus pi over 2. So this is the general scenario, and we can find all properties. Yeah, this is just a function I can plot. So here's the real part. We know all the properties, and we can also study the imaginary part, which looks like this is an odd function. What is crucial here is that the charges, and in particular the energy, just like the quantum mechanical scenario, if we want to assume that these are physical quantities, we want these energies to be real. And this is simply guaranteed, again here a simple one-line argument, is guaranteed by PT-symmetry. So here is the argument for the Hamiltonian or Hamiltonian density, and it follows that the energies must be real when the model is PT-symmetry. But there's a sort of confusing part. It's still a solution when we put this arbitrary parameter to be complex. And we can allow that. So if I take this parameter mu in this solution, it's an arbitrary parameter, and I take it not to be real or not to be purely imaginary, but to be a generic complex number, then PT symmetry is broken. So how does that argument then apply? Well, if we change the parameter in this way, we can absorb this in x, and x can be the shift in x can be absorbed in the integral over here. If I change, if I multiplied or change the parameter in this way, I can also absorb it into t. But since the charges are conserved in time, it is true for every t, and I can absorb a shift in t. But this works no longer when we have n-soliton solutions. So I just showed you one soliton solution, but when we have an n-soliton solution, well, we can absorb a complex part in x and t, but we have n variables in an n arbitrary constants. I should stress that in an n-soliton solution, we can no longer absorb them. And there we have to sort of rely on integrability. But we know that asymptotically, the complex n-soliton solution can be factored into n1 solitons. And then we can use the argument I just showed you before for each individual soliton and absorb the complex shift in either x or t. So it's slightly different. So for these solutions, PT symmetry alone does not guarantee the reality, but it's PT symmetry plus integrability. So, and one can study more. I will not go into this. One can study the properties, how time delays are calculated in these solutions. And I know that some people here are interested in this kind of aspects as well. One can study degenerate solutions, and all this becomes nicely meaningful when you allow solutions to be complex. One can also construct completely new types of models which haven't been looked at before. So here's another example. So this is the nonlinear Schrodinger equation. And we want to look now at higher order nonlinear Schrodinger. So these are solutions. They belong to the hierarchy of this model. And I can add here higher derivatives like this. And if I specify alpha, beta, and gamma to specific values, one gets kind of standard well-known integrable cases, and the one I'm interested here is the case alpha 1, beta 6, and gamma 0 in this term here, and that's what is called the Hirota equation. So here's the Hirota equation, and it's known to be integrable. So there is a zero curvature condition, here it is, and the Hirota equation is coming out. So if you look at this zero curvature condition, you get our two equations. And to make them compatible and to get the Hirota equation, one usually assumes that this function r here, so where did they come from? There were these entries here in this u, that this function r is kappa, where kappa is plus minus 1, times q conjugate. And in this case, this just becomes the Hirota equation, the first equation, and the second one is just the conjugate. So that's the standard way to do it and to derive the Hirota equation. But we have now other choices. If we think about that we might not just want to relate these two equations by complex conjugation, we can also relate them by a p conjugation, meaning x goes to minus x, and we conjugate this q. And if you do this, you also have to redefine a little bit the constants here to make it work. But you just have to introduce some ice in some appropriate places, and then we get what is called a non-local version of the Hirota equation. And you see here, they are now in this equation, there are fields Q located at x and t, and also fields Q tilde that are located at minus x and t. And that's what we mean by non-local. So they are not just fields, they are just located at x and t, but there are also fields in this equation now which are at minus x, same t. And you may imagine there are now different choices. I can also take a T conjugate pair. I can have a really PT conjugate pair where I take this to be the complex conjugate and minus x minus t. And the other options is a P transform and a T transform. And all of them are viable, and the solutions look quite different. Yeah. So they have different types of solutions. They are not just, the concept is very, very, very straightforward, but when you look at the solutions, they're quite different. We know how to calculate solutions. So here is again the Hirota method. We have also looked at other methods. And there are now various options. And maybe I skip this technicality because time is, how much time do I still have?
You have 10 more minutes.
10 minutes. Okay, thank you very much. So I will not explain how the solutions come about, but the point I want to stress is that you have two options now. Yeah? These equations have now new types of solutions, and there are new types of behaviors. So one is, which I call here the standard type of solution, and that consists of, you have your Hirota equations, and then the method, for people who know, and I'm sure there are many people here in the audience who know about it, you have to solve the equations from these factors individually. So we solve, and one should stress epsilon is a formal parameter here. It looks like a perturbation theory, but in the end, the solutions are exact, and we can send eta, the expansion parameter, to anything you want. Yeah. So these solutions are not perturbative, but they're exact solutions. And they come about by solving here these coefficient functions. And in this case, we have 6 to solve. Yeah. And then afterwards, we send epsilon to 1. That's the standard way of solving them. And if you do this, you get this type of solution here. This is just the one soliton. You can do it for other solitons. And you can see here the non-local nature. There's also a correspondence now at minus x. Yeah. So this is q of x and t. And of course, this q tilde in this equation, I just get by sending x to minus x. And if I do this, then I will solve these equations here. Yeah? And you can do this for all 6 variants. Yeah. Now, this was kind of strange when we solved this, because it did not, for epsilon going to 0, we should get the nonlinear Schrodinger equation. And our solutions did not correspond to a solution that was found previously for the nonlinear Schrodinger equation by Muslimani and Ablowitz. So here we struggled initially, and then we found out we can look at this differently. And we set already epsilon to 1 in this last equation. Yeah? So we have only 5 equations to solve, yeah? Where we sort of preset epsilon to 1. And if you do this, you get a new solution. You can check, once you have the solution, plug it back in. This will indeed solve the equation. And that's a different type. You can see it has a really different behavior. It's a kind of rogue wave. Yeah, it has a singularity here. And as t evolves, it becomes infinite. So there are different types of solutions to these equations. And of course, we can generalize this to 2 solitons. Here's a 2 soliton solution. And it looks more involved, but you can see the sort of 1 soliton hidden in there. It's also non-local. Yeah? So the question is, are these solutions meaningful? Are they stable? And so on. And this is something we looked at recently. So here's the key idea of a stability analysis. Stability analysis is probably a subject in its own. Yeah, there are all kinds of techniques. And here I'm just using or introducing a very basic one, very intuitive one. So we have system which is of this general form. Here's our Euler-Lagrange equation, and what you do is you perturb this field. So chi here is a little perturbation, yeah? And then you linearize the Euler-Lagrange equation. So we are looking at linear stability. And if you now assume that this perturbative field chi factorizes in this way, epsilon I to the lambda t, and then some function that now just depends on x, phi of x, then this analysis reduces to the Sturm-Liouville eigenvalue problem, where the potential is here the second derivative of this original potential in my field theory Lagrangian at this solution phi s, yeah, where phi s is a solution of the Euler-Lagrange equation. Yeah. So it all boils down to this Sturm-Liouville equation in this approach to stability. And then obviously when I solve this and I get a real lambda, then we speak of stable solutions, because this will simply introduce a little oscillation on this solution. Yeah. Whereas when lambda becomes complex, then we have growth or decay, and it might just drift away as time evolves. Yeah. So this is the notion of linear stability, and you're reducing the system to a Sturm-Liouville equation. And then the eigenvalues will tell you whether your solution is stable or unstable. Yeah. And here's the analysis of the energy. If you do this for the energies, you also find that the energy of the perturbed system is equal to the energy of the original system. I mean, up to order epsilon cubed. Yeah. So here's, if you just plug this in here, then this is what we get. And the first term vanishes, or the first integrand vanishes, because it's just the Euler-Lagrange equation. The second one is the Sturm-Liouville equation. And the third one vanishes if I ensure some asymptotic properties on my solution phi. So that's then the upshot is that the energies of the perturbed solutions are equal to the energies of the solution themselves up to order epsilon cubed. So let's look at a concrete model, and this is, I think, the last point I will make. So it's the Bulov dot model, which is a very interesting integrable model. It has been studied in quantum field theories because it has a beautiful, exactly solvable scattering matrix, which one bound state, it fuses to itself, and there are all kinds of nice properties to this model. But on the classical level, the solutions here to this Euler-Lagrange equation, and that hasn't been considered before, even if I take this to be all completely real, I allow the field to be complex, but there are no eyes in here. So it looks like a very harmless theory, but the solutions are in fact often complex. So here's the different types of solutions. I will just do the discussion for what we refer to as a type 1 solution. So that's how they look like, the one soliton solution. They have this kind of picture here on the left when they evolve in time, and they're kind of Picon solutions, if you like. There's some singularities here, and you can regularize them on the right. I have chosen, so the left picture is for beta real, and the right picture is for beta purely imaginary, which is nice because in that case, the solution becomes PT-symmetric, as you can see. I pick up an minus from the t from the x, and if beta is real, then it's not PT-symmetric. But if I introduce here an I, then this will become PT-symmetric, and the singularities actually now regularize. So here, this is very regular. The price we pay is an imaginary part. So the dotted lines are imaginary parts. But we know, that's what I tried to argue before, that's not a problem. The energies are still fine and well-defined. They are real. So this is a type 1 solution. So this was phi plus. Phi minus looks a bit different. Phi minus is already complex from the start. If I take here the lower sign, and then we can also distinguish and introduce minus signs by allowing the modulus of kappa to be smaller 3, and then this term will also be complex. And then the solutions look a bit more like breather type solutions. That's portrayed in here. And when we do this analysis, I explained to you, this general analysis of stability, then the associated Sturm-Liouville auxiliary equation involves this potential here. For the plus and minus, they are just related by a shift in beta, so it's okay just to look at one of the versions here. That doesn't look very inviting because we want to find the solutions to the eigenvalue equation, but there's a little trick one can do. This is what I explained before. These were the Darboux transformations. I explained this in the context of explaining spectra for non-emission models, but you can also use this just to solve models. And if we do this here, we can actually map it to a much simpler model, namely this one, the sec square potential. And this potential you can find in Landau-Lifshitz. That's a potential for which the solutions are well known. And we find one bound state with a lambda equal to 3/2, and we conclude from this that the solutions are stable. And we can do this for other solutions. We can do it for the type 2 solutions and elaborate more on this. And there are many interesting things to be said about this, but I will cut this short now. And also, this is much more recent work now. We also looked at the non-local solutions to this Hirota equation, and we have to adopt the method a little bit, but also in there we found that the solutions are stable as well. So they are meaningful, stable solutions, but this doesn't always happen. So we also found some unstable solutions, and it's still not clear if there are some general a priori principles that tell us that certain solutions are stable and others are non-stable. So this is still an open problem we are looking at. And if you are interested in this topic, I should also say we are running since quite a while now a virtual series on pseudo-Hermitian Hamiltonians in quantum mechanics. So here are the details. You're all very welcome to register for this. And there's also proceeding already just published. So there are many papers on recent results in this proceeding based on that series. And if you work in this area and you would like to present something in this series, then please just drop me a note. So thank you very much again for your attention. And if you have any questions, I'm really happy to answer them. Thank you.
Thank you, Professor. It is time for questions. Yes, Nivet, can you unmute and raise your question?
Hello, can you hear me?
Yes,
I can hear you.
So from the first part of the talk, I have a few small doubts. Is PT-symmetry a needed condition to interpret non-Hermitian systems?
Sorry, say again, is
PT-symmetry a needed condition to interpret non-Hermitian systems?
I didn't understand. Is PT-symmetry what condition? And
is it a necessary condition to interpret non-Hermitian Hamiltonians?
Okay. Yes, that goes hand in hand. Yeah. So I would say it is a necessary condition.
Okay. Then can I take a system?
Let me specify this a bit. You say to interpret it. Yeah. No, to interpret it, I'm also okay if I find the Dyson map and the metric. Then I can interpret it and I can calculate everything. Yeah. But PT-symmetry is very intuitive and it's directly there. So it tells you many things, but it's not a necessary property to have. But I would say it's necessary that systems possess this property. I don't know if that answered your question. Yeah. But continue.
Okay, then is it okay if I interpret systems using Dyson map or a metric? The systems that does not have PT-symmetry, then we can still interpret it using Dyson map or a metric operator.
Yes, you can calculate the Dyson map, but that, you see, that Dyson map reflects the PT symmetry completely. Yeah, if you think of the examples I presented, yeah, the Dyson map breaks down when the PT symmetry breaks down. Yeah, so this goes hand in hand. At the exceptional point, yeah, the PT symmetry breaks down, and also the Dyson map breaks down. Yeah. Does that answer your question?
Nivet.
So if you look at this, it's all in here. If you look at this simple example of the two-dimensional system, I think there one can understand all the features. So this one here, yeah. So the PT symmetry breaks down at lambda equal to kappa, yeah. But then also the Dyson map breaks down, which actually here I didn't write down, but for the next example, I did write it down. Yeah. So here you see that this theta here breaks down when modulus lambda is greater than A minus B. Yeah. Then the arctangent is no longer well defined. Yeah. So it's only PT symmetric in this regime. Yeah. But if you want, you may have never calculated the PT symmetry and just calculated the Dyson map. So it goes hand in hand. It's not one versus the other. These are two properties. They go hand in hand.
So since the Dyson maps are our own assumptions, the assumptions we make, can we make a workaround like for systems that doesn't satisfy PT, we can still use a Dyson map and interpret non-Hermitian systems?
What kind of assumptions we have to make on the Dyson map? Is that the question?
Since Dyson maps are purely from an assumptions we take as a mathematical point of view.
Yes.
So the initial assumptions I make, can I use any kind of assumptions to work around this PT symmetric problem, or for systems that doesn't satisfy PT symmetry?
Okay. So here's the problem. Yeah, I give you this Hamiltonian and I ask you find the Dyson map. Yeah, and your question is what assumptions can I make and what assumptions are meaningful. Yeah, so all you have to solve, if we are in the time-independent case, I have to find a map, a similarity transformation that maps me from this Hamiltonian to something Hermitian. Yeah. So this one is nice because it is expressed in terms of generators of an algebra. Yeah. So you don't get out of this algebra expanded by K1, K2, K3, and K4. So the general ansatz you can make, the general assumption on your eta is e to the, let's say, alpha kappa 1 or K1 plus e beta K2, gamma K3, delta K4. That's the most general one you can make. Yeah? And when you now act on this capital H, yeah, you use your Baker-Campbell-Hausdorff formula to expand the exponentials. Yeah, you get something. And whatever you get, you have to impose the conditions that the non-Hermitian terms are 0. Yeah. And you can do this. So there, I just showed you for this one, a very simple one. Yeah. For the talk, I like to keep it simple, but there are more complicated ones. Yeah? So these are the assumptions you can make. Yeah? Whereas if you do not recognize that this is an algebra, you would play around with x and p's, right? And that's more complicated. Maybe you write down here e to the x squared alpha times plus beta px squared plus gamma py squared, etc. And there are much more possibilities if I'm in the if I'm using canonical coordinates. You see what I mean? Then the problem becomes much more complicated. And initially, people did this, and there are some examples like the ix to the power 3. You can't express as an algebra, and then it's really hard to solve this. Yeah. And in fact, that hasn't been solved. That's only known perturbatively. Yeah. So it can be quite a challenge computational challenge to find the eta. Yeah. Does that answer your question?
Okay, sir. I have another question.
Okay.
As thus, can we use just PT-symmetric alone to interpret system and not use Dyson Map? So we can have just a one Hermitian version, or since you said that the Hamiltonians we make due to the assumptions are not unique,
Yes.
can we just not take this Dyson Map conversion and we can just interpret it to PT?
No, it's not unique. I mean, there's nothing that singles out one metric from another. Yeah. If you just start with a Hamiltonian, yeah. But in this paper here, this very early paper, which I think you can see now, this paper by Scholes, Geyer, and Hane, yeah, they already argued about this, and they already understood that this is not unique, yeah, and it becomes unique if you define one more observable, yeah. So if I say in my Hamiltonian, let's take this one as an example, and if you say I want x to be an observable, small x, usually it's not an observable because the observable is eta x, eta minus 1, yeah. But if you say x is an observable, that implies that the eta commutes with the x, and that would make your metric unique. It turns out in this example you can't do this because you will not find a solution. Such a solution does not exist. Yeah. So that's the problem. If you specify another operator, the metric becomes unique, but it's not clear which operator to pick. Yeah. You don't know which operator will work. Yeah.
Okay, sir.
Yeah.
Sir, just another more question. So
Okay.
if I can make n number of Hermitian versions of a non-Hamiltonian, and I can, if I try to define an observable for these n number of Hermitian Hamiltonians, does the physics vary in each of these Hermitian Hamiltonian, or
Yes.
do they all do the same point?
No, they are all different physical Hamiltonians. Yeah, because I would say the physics is what you observe, right? That's the physics. Yeah. And when you have a different metric, you have different observables. You observe different physics. Yeah. So the physics is now no longer defined just by the Hamiltonian. We are used to this. I give you a Hermitian Hamiltonian, and that defines my physics. Now we have to say I give you a Hamiltonian and a metric, or I give you two observables. That's the same. Yeah. But the physics is different when we have different metrics. These are all different theories. Yeah. And it's still a kind of a mystery. We know where this comes from. This comes from symmetries, yeah, of the Hamiltonian. Different types of symmetries, they can be expressed in terms of the Dyson maps. Yeah. And these symmetries will lead to many, many more solutions. Yeah. In fact, even in the time-dependent case, we managed to construct an infinite series of Dyson maps, not even finite. Yeah. So is there a more general principle that joins them all together? Like, are they related via a gauge symmetry or something? So for the moment, I think we can only say they originate from some symmetries. Yeah. But there's not one theory singled out from another. Yeah.
Okay.
Yeah.
So means theoretically it is possible to interpret a system that is broken in PT, like an optical system or any other physical system, and we can convert it to a usable Hermitian Hamiltonian, and we can interpret it in other usable ways.
In quantum mechanics, no. Yeah, in the broken regime, it's broken. There is no proper interpretation. Yeah, in the time-independent case. In optics, is different. In optics, we we can actually generate, or people can, I can't, but people can do this in laboratories and produce waveguides, one with gain and one with loss, and they are balanced out, and that's a PT-symmetric system. So in optics, this works. And also in time-dependent systems, this works. Yeah, that's what I find personally very exciting about time-dependent systems. In these scenarios, you can write down a well-defined metric in all regimes. And there are different solutions. Some solutions, they just work in the PT regime, in the broken regime, or at the exceptional point. But there are also solutions, they continuously work in all three regimes. And you can write down a metric, and it is well-defined, crossing over all three PT regimes. Yeah. So in time-dependent systems, you can do this, but not in time-independent systems.
Okay. Thank you. Thank you. It's a great speech. Thank you.
So questions from others? Oh, I'm not seeing any questions. Let me check with the chat box. No, there is no question in the chat box as well. So since there are no more questions, let me conclude the session by thanking you for accepting our invitation and deliver a beautiful lecture on PT-symmetric nonlinear systems. Thank you, Professor. Thank you very much.
Thank you very much for listening and for the invitation. Thank you.
Thank you.
Okay, thank you. Bye-bye.